So this talk is about cognitive processing and to make a complex network model for them. And this cognitive processing involves here internal mental models that are used in certain complex tasks, and especially for cognitive analysis and support processes. These complex tasks, they often require such internal mental models. They're not only used, but they're also formed and adapted over time. And also the control of these processes is something that has to be done. So this gives a form of modeling where you need, where you can use a self-modeling network concept that we will indeed apply here. We use for the adaptation a number of principles from cognitive neuroscience for first order self-models for the adaptation of the mental models, but also second order for the control. So this is the basic picture of the task that is involved. There is some person in a demanding task like driving, and you monitor the person. You find out what the situation is, whether there is some risk or not. Then if there is a risky assessment, then you consider certain interventions or support actions. That's the idea, and then the whole thing is also adaptive, so you have an adaptation and control over it. So that's how can it be modeled? By a notion of self-modeling network. That's in this case we use a 3-level network. We use the base level where this normal mental model is used. But then you have the first order self-model where the adaptation of the mental model is modeled. And then is the 3rd level with the second order self-model to control these processes. This has been applied here, this setup. So within the first self-model, first order self-model, we use 2 first order adaptation principles. One is from Hebbian learning, like neurons that fire together, wire together. And another one is, relates to the modification of intrinsic excitability of nodes. This is described, for example, here. So these 2 are used at the first self-model level. Then we also use a second order adaptation principle also from cognitive neuroscience literature. In this case, this principle that adaptation accelerates as soon as there is more stimulus exposure. So the general setup is that we have a specification of a network by connection weights, combination function for the aggregation, and by speed factors to have timing that is not necessarily synchronous because of this. So how can a network model itself? Well, it's like this. You add just a self-model to it, and that's a subnetwork with states that represent network structure characteristics. And we have, for example, the following possibilities. You can have a self-model for connectivity, representing the connection weights. You can have it for aggregation or for timing. For example, if you have a combination of these, then you have one connection weight, one threshold for the excitability of some nodes, and the Y node here, and the speed factor. Then you add just a state for them, for each of them, self-model states, so that they can be used as to process with them. Because apparently these are actually parameters, and now we copy them to some variables that can be used to make them dynamic. So that's the way how an adaptive network is created. Just by having this dynamic self-model, you have an adaptive network structure for the characteristics that are in that dynamic self-model. Of course, these self-model states, they have to be integrated in the network as a whole. You have connectivity with incoming connections for the causal impacts on it. You have outgoing connection to effectuate the value of it. And you have, of course, also a combination function to specify the aggregation, and also speed factors for the timing. They have also explicit representations. So for this case, we use this excitability adaptation principle. So this is a state that is added to represent the excitability of this node here of your original network. And that's affected by the activation. The stimulus exposure is just affecting it as well. And then it has its effect because this is used as a threshold value for a logistic combination function used here, so that it represents the excitability threshold. Of course, it also has an application that can be done in a straightforward manner with often used function. In timing, of course, you have to set a value for that too. So the second order principle used is this one. That's you add a state for speed, for the timing of this adaptation. So this is a speed factor representation of the t state here. Therefore, it is second order, as the t state is already first order. And then also that is affected by things from the lower level. And it has its effect on the actual value of the threshold for this threshold, for the speed of this threshold state. So if this is higher, then the speed is also higher. So the adaptation of the threshold goes faster. So that's how it works. Then for this element, of course, also for this 8th state, you have some relatively standard functions that you can use to specify it further. Then we show it how it works for the example simulation. So this is part of the internal mental model for the whole task, and that actually this is the analysis task, and this is for the support task. You see that a number of factors that are monitored, they can lead to assessment of exhaustion risk or of driving risk, depending on what happens. And then this is input for the second task, for the support task, and then you can find there is an advice to rest, or there is an advice to slow down, or actually if the car is doing it itself, it is just doing slow down, or it does blocking start. For example, when there is no driving yet. So that's the mental model for analysis, that's the one for support. And then we make a model, an explicit representation within the network of the structures of these mental models. And these are the connection structures of this model. And these are the connection structures of that model. And then we use the thresholds for these ones and also for these ones. They are the outcomes of these different tasks. They have an adaptive threshold. So then we have these first order self models. So that's for mental, and that's for the mental model for analysis, it's mental model for support. And we have connections, that's how they have their effect. And this is how they are affected by the situation at the base level. So that's the first part, the first extra level. Now we have a second extra level. That's this one. Again, we have this connectivity. That's the connectivity with the blue arrows here now, here also. And now we have the speed factors of these threshold states that's represented on this second level. That's to be able to control the adaptation. So then we have two corresponding models here, self models, second order self models. And those are these ones. Then finally, we will have such a network structure. This is the final network that is used. So let's see what it can do. Suppose you run it in a certain scenario. This is a scenario where we have adaptation is starting now because there is some stimulus of the monitoring data that's coming in. So then because of that, there is an excitability threshold adaptation, so that because there is an adaptation speed that goes becomes higher, and then because of that, there's a good option to do the assessment that it runs successfully. Because of that, we have a start of the adaptation for the support model, and then you indeed see that the thresholds are adapted. And because of that, then we can obtain this support that you want to find. So that shows how it works. I think this is the main thing that I want to discuss. So what we did is for complex cognitive tasks that involve often internal mental models, we have found an architecture, a network architecture at 3 levels. And because these intermental models both are used and formed or adapted, and also in addition control is applied to those processes. So this was applied to a car driver case study where you have analysis and support of how the situation develops with the driver. You've used adaptation principles from cognitive neuroscience for it. And then we have some self-modeling network construction that we used to let it work. All of this was done by modeling, not by programming, as we have a dedicated software environment that's just directly able to run these types of models based on just input a number of tables that are called role matrices, and then runs the simulations. So for more details, you could refer to this, like the software can be downloaded here. You're also welcome to send an email to ask questions about it. There's some place where you can find exercises to learn to work with this software. And this is some general literature. Especially this book, there is a lot of details in what I've taught here. And not this model, but in general. Okay, thank you for your attention, and you're welcome with questions either now directly or by email.